Thanks so much for everyone coming. So I hope you don't mind I don't get on the stage. My kind of knees bother me. I like to wander around. And so if I go up and down the stairs, I'm sure I'll fall and break my neck. So today's talk is on developing some IoT hands-on exercises that I do for Defcon every year in the IoT Village. I've been doing this for a number of years. So I'm hoping you enjoy this. You get something from it. At the end, I'm going to do a recorded demo of this year's exercise and kind of walk through that for you at the end. I was planning on doing it live, but my virtual environment is kind of like wonky. So I thought that would go really bad. So let's go ahead and record the whole thing and then step through it, explain the various steps so everyone learns from that. So my name is Deral. I've been working at Rapid7 for coming up on 10 years. My current role there is I am Principal Security Researcher for OT IoT. What does that mean? So I do everything related to OT and IoT at Rapid7. I function as a manager. I got a very small team of really cool people. And I help our pen test teams developing new testing methodologies and stuff like that around IoT. So let's go. The first 5 years. So like I said, I've been doing this for 5 years, and the exercises we've done cover a large gambit. So 2018, we kind of went through and started teaching people how to do, we did multiple exercises, how to use a logic analyzer, how to interact with UART, Universal Asynchronous Receive Transmit, how to do desolder. We actually tried to do that one. That was a total fail because obviously trying to teach people how to do complex desoldering in a short exercise ultimately turned into a mini train wreck for the most part. And then the last one was like pick processors. So we had an exercise around pick processors. Going from there, the next year, let's go ahead and jump to the next slide so we can go into some of this stuff more detail. Like I said, the first year we had all these exercises, like 4 of them, and everyone had a chance to walk through those. The following year, we did exercises, 4 different exercises on and develop these with exercise manuals, the whole 9 yards, on how to pull firmware from embedded devices. And we covered multiple ones, how to do software SWD, how to do JTAG, which is a subset of JTAG, how to do SPI, how to do in-circuit serial programmer. And we had 4 different devices. We had 4 different debuggers that we had them do this with. So they got their hands across a whole lot of different tools, a whole lot of different devices. Even one of the pictures up there, we actually had one of the wristbands. So it was opened up so they could interact with serial debug to actually pull the firmware off the device. The following year, we got into an attack against the device. So I started ramping it up. I'm like, look, I've shown you how to use the tools, how to do firmware. Let's kind of ramp it up. So we wanted to do an exploit. How do we break into a device to get root level access? This particular device is a mesh Wi-Fi. In this case here, we wanted them to get into like the U-boot console, but the problem is you couldn't get to it. It was, for the most part, locked out. There's a setting in the environment variable. If it's set to 0, it will not give them a chance to break out into that. So we did a thing called a ping glitch. In the ping glitch, they would actually, between U-boot loading and U-boot loading the kernel, there is a fine few milliseconds that if you ground out the communication line to the actual flash, the device will error out and drop you into a U-boot console. So we showed them how to do that, to ping glitches by shorting this out during the boot process to gain access, and then from there make some alterations to eventually gain full root access to the device. The following year, I think was 2020, I missed that one, Defcon was canceled for real, which is kind of interesting. But we did a bunch of stuff online. So we kind of circled back and did things online, covering the first year's exercises, logic analyzers, things like that. So then we went on to this year. So I'm going to walk through the whole process to how you get these exercises developed up. In this particular case, We wanted to do something different. We wanted to build on previous years. Also wanted to have it so they can get kind of root level access to an actual device again, but I wanted something new. So I started thinking through this. What would we want to be able to do new? What I wanted to do was, hey, can we do a memory style attack? So I started doing research. Okay, how would this take place? My first initial attempt was I wanted to do JTAG. The concept was within JTAG, I wanted to be able to interact with the device and alter its memory to execute some kind of code or bypass some kind of setting to gain root level access. So I kind of start that whole process of finding devices that fit this model. And it follows that loop: research, buy, test, throw it in the trash, and start over. And this was like really crazy bad. Last year, to step back to last year, trying to avoid that. The previous year, we did the attack to actually gain access to the device. That would involve reading settings, changing settings on the device. The particular device we had that year was a modem. In that particular case, and in every year, we don't want to make the attack something you have to bring with you other than hardware testing. We wanted you to be able to actually attack the system using the software on it. Since it was a cable modem, we wanted to be able to boot the thing up, break into it, make alterations to the system. So we actually connected in using an SD card breakout into the device. In that particular case, it didn't work. I labbed it up, went through the whole thing, and it failed. Everything was working, but when we got to basically the root console of the device, we had no prompt. It didn't work. So I contacted tons of people that are in the whole cable modem hacking community on how to do this, and they literally told me, you can't do that. You have to install your own firmware to accomplish that. That's how we always do it. I'm like, well, that's not doable. This is something what do we learn just by putting our own firmware on the device? We want to break into it and get access to the existing vendor-driven firmware so we can do other testing attacks and things like that. So what was happening was I was getting to like a SSH connection, and all the settings and everything was saying you have a valid SSH connection, but I never had a prompt. Well, apparently in SSH, and I can't remember the switch right now, you can actually alter the SSH's environment structure. What was happening on the device, the vendor had put all these protections in place. One of them is they created an environment that if you enable this on the device to get root level access, they set an environment variable that had no prompt. So even though you got to the system, you couldn't get a functioning prompt. So I'm like 2 weeks away from Defcon going, oh, hell, I'm in trouble. Worked all day one day, and a friend of mine goes, hey, there's this SSH environment variable set that you can actually set your own environment. I'm like, cool, let's try that. I did that, it failed. And I'm like, one more test, and then I'm going to panic and try to find another solution for Defcon. Well, it turned out that if I set that variable not to have my own environment, but to disable all environment structures, it worked. I got a blank screen, but it took commands and executed them at root level. So we didn't get a typical prompt where we got it to work. So I wanted to avoid that this year. So I started early through this whole test process. And we went through a number of different devices. Upper left-hand corner, we looked at a Ring home alarm system. Took it apart, dug into it, hacked into it, found out they had disabled all JTAG on it. So I took that $100 worth of gear, threw it in the trash. Moved on to the next device, which was some kind of smart plugs. Same way, it had functioning stuff, but there was no data sheet. It's one of the biggest problems. We get into OEM devices, so there's no data sheets for the processor. So then I got down here to that OTT box in the lower left-hand corner, and the one I had sitting in my lab, because I always try to use gear I have sitting around in my lab to avoid spending unnecessary money. So I got into that device, and I'm like, cool, it's running a 905 processor. It has a functioning JTAG. Cool. Are there more of these on the market? So I go out with that device and find out none. None of them available in the market. eBay, there's no used ones on eBay. I'm like, I'm screwed. So I go out and find another vendor that produces a similar device with a 905 processor, and I order several of them because I think I got the right device. I'll be able to figure this out. So I bring in about $100 worth of gear. I open it up, and it's a 905 processor, but it's a 905D processor, not a 905B processor. It turns out that processor basically is totally different pinout. I think it had like 48 pins versus 24 pins. Why the hell they called it a 905, I don't know. It wasn't even the same processor in any way, shape, or form. And there was no data sheet for it anywhere on the market. They had OEM'd that processor. So again, it was like, okay, I'm not going to spend days or weeks trying to figure this out. I need a functioning JTAG, and I need one with a data sheet. Threw that in the trash. And during this whole process, I'd also, that camera sitting in the middle. I'd found that camera, had played around with it, really no JTAG. The processor didn't have any data sheet, but I did find something that was interesting in it. So that was kind of a memory alteration type attack. That was published online, so I utilized some other people's research in this. So I set it aside, and I continued down the JTAG. So when I hit that demarcation point, it's like, you find a solution, or you're going to have to go back. So we tested another device, the wireless smart gateway, same problem there. We get the device, we take it apart, looks like a good candidate. Turns out that JTAG's disabled on this processor. We can't go in and re-enable it or any of those type of things. So instantly I kind of back off. I'll go, okay, let's go ahead and dig into the actual camera and try to develop an entire test process for that. So we take the thing apart. It has a simple memory example, and it's cheap. This is cool. This thing's like $15. So I immediately bought a whole freaking shipping crate of these things, like 12 of them or whatever, and I'm shipped to my house, and it cost me $140, $150. Like I said, cheap. They're like $15 a piece on these, and I took them apart, and I started whacking away at it and go, okay, we need to develop an entire process where we could go through this thing and teach people. So we have to add other pieces to the puzzle, more than what was actually published online. So we take it apart, and it's cables inside of it, rip all that off. We don't need all of the extraneous gear. The main thing we're after to get level access to this in a test environment is we want to actually have a device where the CPU is running, memory's running, and we can interact with it in some fashion. So we can disconnect almost everything. So we get into doing that, and we start looking at the device. So we have a CPU. This is, it says 38WX1. This happens to be XM530 processor. Very common processor used in very cheap Chinese-made hardware out there. So that's good. Another cool thing, it has a SD card on this device. That means if we want to get firmware off the device in a training environment, we can simplify it. We can teach people how to read it off the flash and eventually write it out to the SD card as part of the process. And then from there, we can pull it over our operating system and do whatever we need to do to it. We also, it turns out it has a 1.27 millimeter header. I don't know if anyone here does any hardware hacking type stuff. In my lab, I have the tools for everything. No matter what the header is laid out on the device, I have ways of doing that. But that has its own problems. It's small. It's very small. It's difficult. Most test leads don't really attach well to that header. Most test leads are often designed to better connect to 2.54 millimeter headers. And then we have a Wi-Fi. Didn't really need to utilize the Wi-Fi, but I wanted to point it out, the Wi-Fi device in here. This is kind of cool. I've been looking at a lot of these cameras, and not to divulge off onto something else, but again, I always do research and thinking of new ideas and ways. This device is actually communicated to from the camera structure processors on this device using USB. So it's in-circuit USB communication, which is something I'm looking into. It's really fascinating. If you ever dug into the USB standards or how USBs are laid out on a circuit board, it's insane. High-speed USB is so impacted by noise and communications and stuff like that, especially in circuit communication. How they define these on the circuit board is amazing. The runs and the ground lines have to be certain micromillimeters apart and all this type of stuff, or the communication won't work. So in the future, one of the things I'm working on is how to interact with inter-chip communications on USB in circuit. So hopefully we'll see something come up in the next couple of years on how to deal with in-circuit high-speed USB communications for intercepting, because you can't throw a standard logic analyzer on this thing and capture it because it's such high speed. Most of them don't run at that speed. And then we have flash memory. So this one's nice. If you want to get the flash memory off this thing, you can always just pull it right off the chip. But I don't want to make that part of the exercise. That can become problematic. If you're dealing with an I2C communication chip, it's fairly easy just to piggyback a clip on there and read it because the interaction with that is channel-based. So most of the readers will actually allocate the channel for reading the data, but if it's SPI, you run into a problem with piggybacking sometimes because the actual CPU will keep grabbing the SPI from you, and you have to set the CPU to reset sometimes to actually be able to read that. And then the only other alternative is to actually pull the chip. And I'll be honest with you, if I'm working on this device here myself in my lab, I've got to the point with my solder, desolder skills, I can desolder that chip, pull it off, read it, and put it back on in less than 10 or 15 minutes. I've gotten efficient at it. Sometimes that's easier than trying to track down a JTAG or deal with other methods. I can often just desolder the chip and read it. But for training purposes, that's really not realistic. Either one of those adds some level of complexity. And our exercises, we want those to land within a 15 to 30 minute time frame. We set up multiple stations at Defcon, and we run hundreds and hundreds and hundreds of people through these exercises. So if it starts getting dragged out to an hour, we can't get as many people through the exercises, and we want to educate and train and give people that experience of interacting with IoT hardware. So we had to take that out and look at other methods as we get into, let me go back here real quick. Also, the other chips you see, the lower one down there and one slightly to the left on the side right picture. One of those is it's kind of a weird motor controller, even though there's no motor control stuff on here. So I think it's being used as an A to D conversion chip is how that's functioned. And the other one is associated with some USB communications coming out of the device. Okay, so how do we deal with the 1.27 millimeter in training? I always like to make things simple. Well, there's gear for everything out there. So we just kind of go out and we buy one. So it's a 1.27 to 2.5 millimeter. This makes life so much easier. These things are cheap. You buy them in bulks of like 10, $1 2 piece. So I have a crap load of these in my lab for, hey, I don't want to deal with this. I just solder this on there and take care of that problem. So we solder that on there. There's 4 leads. You can see 4 leads soldered up there. So we have UART communication here, ground, transmit, receive. The one that's not connecting is voltage. In this case, it would be 3.3 volts. And you really don't need that to actually interact with the device. Just ground, transmit, and receive is actually needed in the process. So we have to build the exercises. What's involved in that? So once we've developed all of the main steps of the exercise, we have to build hardware. So I'm going to look at the picture, and I have a tendency to, at these conferences, I like people to be able to get a closer look at it. So here's a couple of the cameras. I'll pass these around. And here's the actual device test boards we set up. I do this every year. The cool thing is this year I thought, hey, man, it is Defcon, let's put it on black acrylic. The worst freaking thing you could ever do. You know, we're all like paranoid of disease and infection. This stuff shows every piece of dust, every fingerprint. You know, if someone anywhere near the coughs is going to show up, and you're thinking, oh, what was you thinking, Daryl, when you put this thing together? So I'm sure you're not going to get anything from it because I'm like disease-free, but here you go. And then here's a couple of the camera devices you can look at. As you pass these things around, take a good look at them. I ask you to be careful with them. That device, batteries will be used at Defcon. So when I get out of here, I got to go back and retest these, make sure they work. So try not to drop them, bang them, pry chips off it with a pair of pliers in the back of the room, or anything like that. So from there, what do we need to do? Multiple things. We need to build these, build 12 of these. So I go through, buy all the gear for this, and assemble all these things in my lab. So we get that built. The goal of building these things is we want it easy for the user to interact with, and we want it easy not for them to destroy the devices. So we found out mounting them on these things is pretty good. So we'll see how that turns out this year. Last year, I was terrified. The exercise was complex because when we were putting the SD card connection into the device where we tap directly into memory on the embedded multimedia controller with an SD, we backfed power from the SD card reader into the device. It would power up the embedded multimedia controller and the flash memory, and that's all it would power up. That was all the juice, the way the circuit was designed, it allowed us to do that. The problem is if you had that plugged in and the person doing the test plugged power into the unit at the same time, the smoke got out. So there was no physical smoke, but it destroyed the device. Okay? On top of that, we also had them pulling memory off, altering it. They DD it off the device, they would alter it, repack it, DD it back onto the flash of the device. So what could go wrong there, right? The fear there was, while we're doing this, they're often communicating over dev SDC, which was the SD card reader on the device that we were bringing up. But if they put in SDA, they could literally overwrite the hard drive on the laptop with flash memory from the device. So I'm thinking, will we survive Defcon this year? We actually made it through all of that with 10 devices, and we only lost one device. We had one gentleman who's like, hey, this exercise is not working. I went through everything. I walk up and he has both power and the USB plugged in, or the SD card reader plugged in. I'm like, first, you've burned the device out. On top of that, he overwrote the hard drive with the flash. So the same guy did this. So you know, you're thinking, this guy works for somebody. I feel sorry for his employer because the exercise was very detailed. Every page had big red letters. Do not plug both sides in. And then also do not type in SDA or anything like that. Always look at the drive you're writing back to. But he still managed to totally smoke the device. So we kind of laughed that off, threw everything aside because we did have some backups, so we were able to survive that. So the ultimate goal is we want to avoid that. And then I write up a manual. This year, the manual, I think, is like 18 pages, 20 pages. It's like a 20-minute exercise. So not only do we want them just to follow the exercise, because it becomes too mechanical like that, we want to add content into this. So we explain things. We explain things like the boot process. We explain things like why we did this and why we did that. So it becomes a real learning exercise and not just a mindless click, 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 click. And it goes pretty good, and we've been very good at actually developing these things out. I would give a shout out. So when I was doing this research, looking at this device, the XM530, this gentleman here actually went through the hack for the most part that we're going to use. He was using a different camera. The offsets were completely different on the device. It was the same attack, but a different device and different structure of that. Plus, all the stuff we built into the overall exercise was not actually done in his. But I want to give him a shout because what he did helped me speed this up a little bit. So now I want to go through and run through the actual demo of the device. Yeah, I think we got it. Let's see if this will work. Okay, so the first thing that happens to be an FTDI, which is basically TTL, UART connection to USB. We connect it to device. We hinge the actual device so that you get access to the SD card. So during the exercise, I need to plug everything up. So we'll power up that device there, and I'll hook to a laptop we provide with all the software and everything on it. And then from there, we're going to go through, we're going to fire up a GDK term, a terminal, so we get UART access to the actual device. And then we power up the device once we configure it. So they have to go through the whole configuration process, set up the port. They have to pick the TDY USB that actually shows up on the device. And then once they power up the device, this is what they initially get. As we can see, oh gosh, this thing doesn't want to work. Hold on a second. Get this running again. I think this will work. So at the bottom, you can see it says done booting the kernel. Well, they don't get anything else. They don't get a prompt. They don't get access. That's all they get. But we also see up the top, it says press Control-C to stop auto boot. What that'll do is drop them into a U-boot console. So there is a setting environment variable called boot delay. Boot delay has to be set to something higher than 0. If it's set to 0, they'll never get that prompt, and they won't be able to break out that way. And they'll have to do that pin glitching thing I mentioned before. So so we've gone through, and I have them go through and look at some of the stuff once they break out. Control-C, they break out into it. And I have them look at environment variables. I have them look at commands that are in the system so they get an idea of what they're looking at. This actually controls the whole U-boot process. The environment variables let you set all that structure to define that. So in this particular exercise, what we want to do is we want to set XMUR equals 0 in the environment variables. This will allow the device to continue on past kernel load and give you a prompt. And we go ahead and we type that in and we check the environment variables and we can see that there is no XMUR in there. It will not let us make this setting. So this is where the memory hack will come into place. So the first thing we want to do is we want to be able to have them get the firmware off the device. So have them put an SD card in there and we'll go back into the U-boot console and we will have them interact with the U-boot console commands to actually pull the data off. Now U-boot's compiled differently for different devices. So you don't always get all of the functioning commands. But in this case, I have them look at some of the commands. The first one is SF. SF will have them the ability to basically destroy the devices they want to brick it. But SF probe has to be run. SF probe will set up the interaction within U-boot to allow interaction with the flash memory. So it sets up the bus or turns the bus on for that level of communication. So then once they run SF probe, we're actually going to have them read memory or read flash into RAM. They're going to read it into an area RAM. In this case, they're going to be reading to address 81 whatever, starting at 0 from 8,000 from the flash memory and put it in memory. So now it's in memory, you need to move it to the SD card. And the way to do that is through an MMC command. So have run the MMC, show the command structure there, you can read, write. There's also a command called MMC info. I'm showing that to you. They are not doing that. You don't want them doing this. So now we're actually going to pull it from RAM, we move it from flash to RAM. Now we're going to move it from RAM to the SD card, reading at 81,000 or 81 million, and also move it in blocks. So 4,000 is a hex for blocks, 512 byte blocks. Now they have that, we have them pull the SD card out. They'll move the SD card over to a standard reader on the actual laptop. Trying to make sure we have enough time for this. Get through it. So it's a fun exercise. And from here, they're actually going to open up a new console. They'll also open up disk on the device, on the Ubuntu image. On disk will give them the ability to actually see where the SD card's mounted up, whether it's on dev SDB, dev SDC, dev SDD, whatever the case may be. So they need to define, so they read it from the right location. And then once that's loaded up, they'll be able to, here we're looking at it happens to be SDC in this particular case. And then they'll go over here, and they'll literally do DD the image off of it. So that's going to be a bit level copy. It's going to read it from dev SDC, and we're going to write it out to a file. In this case, this won't be in hex. It will actually be written out. The command will actually use standard decimal. We'll set the block size to 512, and we'll actually read actually 16,000 some blocks, which is 8 megabyte. That's on the actual SD card of the data. Now, when this is written out to the actual SD card, it's not an SD card you can plug in and it's going to mount up. It's just bit level written, so there's no structure, so they have to read it off this way too. And we can see we created an image.bin, which is 8 meg in size, and then we're just going to run binlock on it. Now we have the firmware on there, and we explode the entire firmware out. The perfect situation would let them hunt through all this firmware and try to find the Etsy password, but this is a big blowout of data. So we're just having them jump to the folder that blew out to, which is a CramFS root, and we're actually going to have them go through looking at the hash that's in there, because we need the root password once we get a root prompt. In this case, we have them run John. And since John's already been ran on this and busted, we know what the password is. So now we know what the root password is. Again, you could find this on the internet if you want to hunt around for the XM530s. It's almost always the same on every device. But again, I want to expose them to different tools, different ideas, things that they're going to use. So they get to use John, and then at that point, we're going to jump back over and we're going to do something different. Remember, this is a memory alteration attack. There's a filter somewhere in running memory for XMUART, and we need to find out where it's at. So we literally open up the binary file in hex edit, and we search for, under the string setting, XMUART. Turns out there's only one XMUART written in here, and we need to find the offset address for it. So we see it right there, and the offset address is 1D7FD. So they'll go through, they'll find this offset. Now, once we get the offset, we need to find out, here in a minute, we'll get to it, where U-boot is loaded in memory on the actual device. So we'll jump back over to U-boot console. And we'll run BDinfo. BDinfo gives us this information. If we look up there to relock address, that is the starting memory for U-boot. The way U-boot works is, how the boot process works, a ROM, a first bootloader, ROM will load a first level bootloader in. That first level bootloader will initiate RAM on the device, dynamic RAM, okay? And then it will actually load U-boot into memory on the device and put it in a relocation address. So now you know where U-boot's loaded, and we have our offset. So we just need to add the two together, and I have them do this. I give them a calculator set up properly, but I also tell them how to do it from the command line with printf command, which you can do with printf command, which it seems like every time I do it from printf command, I totally screw it up. So we'll see how that goes for them, because I always mistype it. It's so much easier in a calculator. So now we find out where XMUART is. We read the memory location in real memory, and we can see, since we had the base address, the offset, we put them together, we know XMUART's in wide memory. Now we're going to overwrite that filter. All we have to do is change the first character in filter. So we're going to change the X in XMUART to an A with the 4-1. And then we run it, we look up in the right-hand corner there, it says AMUART. So now when we go to make alterations to the device, That filter's not going to work anymore because we've altered it in running memory. So now when we set environment variable XMUR to 0 and type it in right the second time, we can go ahead and now we can go print environment. And we see our XMUR as at the bottom of the screen. We're actually able to overwrite the environment variables because we altered the filter in the device. Now we go ahead and save it and we run reset. And we get a different boot process. Instantly, the system starts booting up. Now we've bypassed that filter, giving us access to eventually get to a logon prompt on the device. So once it boots up to a certain level, it'll actually stop scrolling stuff, hit enter a couple of times, and you just get a login prompt. We know the root password now because we cracked it. Now we can put the root and the password in there, and the attendees will now have root access on the device, going through this attack process on the device. So it shows an example. If you can get access to any kind of running memory on the device, you have the ability to alter its functionality. Hopefully next year I'll have a JTAG version of this, because what I want to actually do, I'll tell you, but don't hold me to it if it totally fails. The goal is next year to do an exercise with JTAG where we actually inject shellcode into running memory with JTAG and then jump to it to get root level access on the device. So that's my goal for next year. That was my goal this year, but again, I kind of ran out of time and I probably blew $200 or $300 on gear, and I figured it's time to pull that back and solve that problem. So as you can see there, we get to that. I'm going to go ahead and just let that continue running. And in case here, so here's my contact information. At the bottom is a link to my blogs. Every year we run exercises at Defcon. I write all of the exercises up in the blogs. So all this data is recorded out there eventually after Defcon for those who want to repeat it. And other stuff that I've done. There's some great blogs out there on different methods and different things on various things, from reading using JTAG and serial debug on devices all the way to these root level attacks on embedded hardware. This has been a fun process. Again, it's a lot of work. You start thinking about it, it's very time consuming to do this. So who's all going to Defcon this year? Okay, we have a few people. Please show up over in the IoT Village, go through the exercise, let us know what you think. I'm always looking for feedback. For those not going to Defcon, I also do these exercises at a conference called Hackers Teaching Hackers in Columbus, Ohio in November, which is a great conference. It's a 2-day event. One day is like all village type stuff, and the second day is talks. It used to be known as 614Con, and we changed it to Hackers Teaching Hackers. And again, that's like the first weekend in November, if I'm right. And I think we have a few minutes. Are there any questions? No questions. Is it like that early in the morning?
No. I've had 4 Red Bulls already.
Yeah, that's what I'm thinking. I hope you enjoyed it. Did you enjoy it? Okay, that's good. I won't be around here all day. If you want to talk hardware hacking or anything, please come up and say hi. And if you have any questions and you just didn't want to ask them in the room, please grab me somewhere out here today and ask me questions. And thank you very much for attending. I know it's early. I don't know how late you were in the casinos last night. Hopefully you didn't lose all your money, drink all the beer. Save some of it for me and my friend Nate for later. But thank you very much for coming. I greatly appreciate it.